Chapter 1.5.6 Network Policies. To control traffic flow at the IP address or port level for TCP, UDP, and SCTP protocols in Kubernetes, consider using network policies for specific applications in your cluster. Network policies focus on how a pod is allowed to communicate with various network entities, excluding common terms like endpoints or services in Kubernetes. These policies apply to connections with pods on one or both ends and do not affect other connections. Network policies are based on identifiers such as other allowed pods, namespaces, and IP blocks, with exceptions like traffic to and from the node where a pod is running. By using selectors or IP blocks, network policies define what traffic is allowed to and from matching pods or namespaces. Prerequisites. Network policies are enforced by the network plugin and require a networking solution that supports network policy. If a network policy resource is created without a corresponding controller implementing it, the policy will not be effective in controlling network traffic. The two sorts of pod isolation. In the context of pod isolation, there are two types: isolation for egress and isolation for ingress. Isolation for egress refers to restrictions on outbound connections, while isolation for ingress pertains to limitations on inbound connections. By default, a pod is non-isolated for egress, allowing all outbound connections. A pod becomes isolated for egress if there is a network policy that selects the pod and includes egress in its policy types. This means that only connections allowed by the egress list in a network policy will be permitted. Similar rules apply to isolation for ingress, where a pod is only allowed connections from its node or those specified in the ingress list of a network policy. Network policies are additive, meaning they do not conflict, and the connections allowed for a pod are the union of all applicable policies. For a connection between two pods to be allowed, both the egress policy on the source pod and the ingress policy on the destination pod must permit it. If either side does not allow the connection, it will be blocked. Therefore, the order of evaluation does not affect the outcome of the policy. The Network Policy Resource. The Network Policy Resource in Kubernetes allows users to define network policies that control the flow of traffic to and from pods within a namespace. Mandatory fields for a network policy include API version, kind, and metadata. The spec section of a network policy contains information defining the policy, including pod selector, which selects the pods the policy applies to, and policy types, which indicate whether the policy applies to ingress, egress, or both. Ingress and egress rules can be specified within a network policy to allow or deny traffic based on specific criteria, such as source IP addresses, namespaces, or ports. An example network policy provided isolates pods with the label role EastDB in the default namespace for both ingress and egress traffic. Ingress rules allow connections to pods with the label role DB on TCP port 6379 from certain sources, while egress rules allow connections from pods with the label role DB to a specific CIDR range on TCP port 5978. For further examples and guidance on declaring network policies, users can refer to the Declare Network Policy walkthrough. It is important to note that the effectiveness of a network policy may depend on the chosen networking solution supporting network policy enforcement. Behavior of to and from selectors. In Kubernetes, there are 4 types of selectors that can be used in the ingress and egress sections of a network policy: pod selector, namespace selector, and pod selector, and IP block. The pod selector selects specific pods within the same namespace as the network policy for ingress sources or egress destinations. The namespace selector selects entire namespaces for ingress or egress. Combining namespace selector and pod selector allows for more specific selection of pods within specific namespaces. The IP block selector is used to define IP CIDR ranges for allowing ingress sources or egress destinations, typically for cluster external IPs. It is important to note that in Kubernetes, the source or destination IP of packets may be rewritten by cluster ingress and egress mechanisms. This means that the behavior of network policy rules based on source IPs may vary depending on the network plugin, cloud provider, or service implementation being used. It is recommended to use kubectl describe to verify how Kubernetes interprets network policy rules, especially when dealing with IP-based rules. Default policies. In the context of network policies within a namespace, the default behavior allows all ingress and egress traffic to and from pods within that namespace. However, there are options to change this default behavior. One option is to create a default ingress isolation policy by creating a network policy that selects all pods but does not allow any ingress traffic to those pods. This ensures that even pods not selected by any other network policy will still be isolated for ingress. Alternatively, if you want to allow all incoming connections to all pods in a namespace, a policy can be created that explicitly allows that. This policy will override any other policies that deny incoming connections. Similarly, default egress isolation policies can be created to deny all egress traffic from pods within a namespace or allow all outgoing connections from pods. Lastly, a default policy can be created that denies all ingress and egress traffic by combining the previous two policies. This ensures that all pods within the namespace are isolated from both ingress and egress traffic. Network traffic filtering. Network policy is specifically for Layer 4 connections, TCP, UDP, SCTP, with behavior varying for other protocols across network plugins. CNI plugin support for SCTP protocol is necessary. A deny all network policy guarantees denial only for TCP, UDP, and SCTP connections. Behavior with protocols like ARP or ICMP is undefined. Allow rules for specific pods may have undefined outcomes for protocols like ICMP. Targeting a range of ports. Kubernetes v1.25 introduces a new feature that allows users to target a range of ports in network policy configuration instead of just a single port. This is done using the endport field in the network policy YAML file. For example, a rule can be set to allow communication between pods labeled as roll-db on the default namespace with any IP in the range 10.0.0/24 over TCP, with ports between 32,000 and 32,768. Restrictions apply, such as endport must be greater than or equal to port, both ports must be numeric, and the cluster must be using a CNI plugin that supports the endport field. If the network plugin does not support endport, the policy will only apply to the single port specified. Targeting multiple namespaces by label. In order to target multiple namespaces with an egress network policy, you must first label the target namespaces. You can do this by adding the labels under Namespace Selector in your network policy document. It is important to note that you cannot directly specify the names of the namespaces in a network policy. Instead, you must use Namespace Selector with match labels or match expressions to select the namespaces based on their labels. This approach allows you to apply the network policy to multiple namespaces based on their labels. Targeting a namespace by its name. The Kubernetes control plane assigns a label to all namespaces with the value being the namespace name. Network policy cannot target a namespace by name directly, but the standardized label kubernetes.io/metadata.name can be used to target a specific namespace. Pod lifecycle. The text explains that in clusters with a conformant networking plugin and a conformant implementation of network policy, there may be a delay in applying network policies to pods. This means that when a new network policy object is created, it may take some time for the network plugin to handle it. As a result, pods affected by the network policy may be started without protection initially, and isolation rules will be applied once the network policy handling is complete. Network policies apply to all containers within a pod, including init containers, sidecar containers, and regular containers. Allow rules are applied after isolation rules are enforced, which could potentially result in a newly created pod having no network connectivity if allow rules have not been applied yet. To ensure pods have the necessary network connectivity before starting, init containers can be used to wait for specific destinations to be reachable. It is important for pods to be resilient against varying network connectivity, as there is no way to predict the exact timing of when network policies will be implemented by the network plugin. In some cases, pods may experience inconsistencies in how network policies are applied, potentially causing delays in reaching certain destinations. Overall, the key takeaway is that network policies should be considered throughout the entire lifecycle of pods, and precautions should be taken to ensure proper network connectivity for pods. Network policy and host network pods. The behavior of network policy for host network pods is not well defined, but there are two main possibilities. The first possibility is that the network plugin can distinguish host network pod traffic and apply network policy to them just like it does for regular pods. The second possibility is that the network plugin cannot properly distinguish host network pod traffic, so it ignores them when matching pod selector and namespace selector. In this case, traffic to from host network pods is treated the same as all other traffic to from the node IP. This is the most common implementation, when a host network pod is selected by spec.podSelector or a pod selector or namespace selector in an ingress or egress rule. Their connections will be treated as node connections, and rules can be applied to them accordingly, such as allowing traffic from a host network pod using an IP block rule. What you can't do with network policies, at least not yet. In Kubernetes 1.31, certain functionalities are not available in the Network Policy API. However, potential workarounds include using operating system components such as CLinux, Open vSwitch, and IP tables, or Layer 7 technologies like ingress controllers and service mesh implementations, or admission controllers. Newcomers to network security in Kubernetes should be aware that certain user stories cannot currently be implemented using the Network Policy API. These include forcing internal cluster traffic through a common gateway, handling anything TLS-related, node-specific policies, targeting services by name, managing policy requests fulfilled by third parties, applying default policies to all namespaces or pods, advanced policy querying, logging network security events, explicitly denying policies, and preventing loopback or incoming host traffic. Workarounds and alternative tools may be needed until these functionalities are available in the Network Policy API. Network policy's impact on existing connections. Changes to network policies affecting existing connections may or may not take effect, depending on the implementation. If a policy modifies connections, the network plugin determines whether existing connections are closed. It is advised not to alter policies, pods, or namespaces in a way that could impact existing connections to avoid potential issues.